lecture for Rodrigo. Very pleased, so please begin.
Whoops, I was muted there. Okay. Thank you. So before we start with lecture number 4, comment or correction on the last lecture. I'm not the best with literature, and as it turns out, the geometric formula for the LSC relation that I presented to you in the form that I presented to you was already out there, and actually Professor Chong, among others, had put it out last year with Eset and Parra Martinez. I did not know about this reference. Now I do know about it, and just to set the record straight, it was there first. Okay. Today we'll finally come to the point of the distinction between our two EFTs, this linear versus non-linear realization, and we'll put our hands on a very specific example so that you can see, taste, and smell what these theories look like. And also I'll try to be not to extend too much. I know you guys have a long afternoon ahead of you today. So hopefully I'll give you a bit of a breather between this and the next lecture. The point where we left off last time was finding there was this correlation between curvatures in the SMEPT leading order limit. We tried and extend this to higher orders, dimension 8 and beyond. That correlation was lost, so that we couldn't find a definite prediction. Let's just now examine what are the implicit ingredients that go into SMEPT that will help us identify when it is not applicable. So something that we're assuming implicitly in here is that these functions a and b have a Taylor series around 0, that is around h equals 0. So we're expanding them, and indeed that is in the power counting formula of SMEPT, we expand over h over lambda, which implicitly assumes that h equals 0 is a good point to expand around. Nevertheless, the true vacuum is not sitting at h equals 0, but at a finite BEV. Dagger h equals, in general, a BEV that is not exactly the electronic BEV. And that is in opposition to hep, where we assume that we are expanding around the vacuum, and in particular, our little h is truly the field that excites Higgs bosons. But then that key assumption of SMEPT that there is a good analytic expansion around h equals 0 is the crucial thing to realize to have a linear realization. And this follows from the lemma that was already laid out by the very same CCWC authors that we whose formalism for goldstones we already use. And it reads something as simple as this: when do we have a linear realization? Well, if there exists a fixed point in the manifold with a smooth neighborhood, then the theory admits a linear representation. But as with any mathematical lemma or statement, we have to understand every one of the concepts that go into it. So first, what is a fixed point? A fixed point in our scalar manifold is a point that stays the same under a transformation. That is precisely the point h equals 0, as we can see explicitly with a transformation acting on the Higgs tablet, if we're in SMEPT, around with some group element G. The transformer field will be G times that Higgs tablet H, and this will be a different point from the original H, unless H equals 0. in which case you start at 0, you end up at 0. This is comprehensible, again, using geometry. If you think of a plane and rotations around the origin, that system has a fixed point, which is the origin itself, that stays the same. Under this rotation, this is nothing but the generalization for that for a complex doublet. Not only that, but it has to have a smooth neighborhood, and by that we just mean that it doesn't meet this expansion in powers of the Higgs doublet. And then saying that it admits a linear representation is saying that it, in our case, we recover SMEFT. So this is driving home the same message. If we have rotation in a 2D plane, it's only the origin that will be that h equals 0. That is a fixed point, and that is indeed the key to having a SMEFT. But as you know, we don't live there. We live some ways away in the vacuum state there. So the presence of such a point is very hard to tell from where we see that, because we expand around that space. We can only know a neighborhood around it. But this also tells us, this same lemma tells us when we're not in SMEFT, just by violating any of those conditions that we impose to obtain SMEFT. And roughly speaking, we can classify our theories depending on which of these two conditions they violate. It could be that such a point simply does not exist. You could think of that plane removing the origin, making a hole in there would do the job. Although to make it smoothly, you would have to continue it downwards. Or it could be that that fixed point exists, but it is singular. It doesn't admit an expansion around that point. Those are the main two classes. It should also be said that we'll see next a theory of the type B, which are the ones that are better known to date. We don't have UV completions for theory of the type A, and don't have that fixed point simply missing from the amplitude. But that doesn't mean that they don't exist. But most of the theorems and knowledge that we have is about this type of theories. So now we have this lemma. This actually is the answer to our question. So how to tell them apart, but putting it into practice takes a bit more than just stating it. So before we go ahead and look at one of these theories, or a toy model that will actually extrapolate between SMEFT and quotient theories, it's good to pause and actually revisit the question by Pyong Wong before. What type of theories are on each camp? And as it happened, most of the theories, the VSM theories anyway, that you're familiar with, they all fall in generically in the SMEFT camp. So both supersymmetry, say the seesaw model for neutrino masses, grand unified theories, but also composite Higgs model, or even exotic possibilities like non-compact groups, they all belong in SMEFT. And this can be described, but it has actually been done, provided the masses of these particles are heavy enough. You can write as SMEFTs, and if you can push them further and further up, then those SMEFT effects will be ever smaller. And that's actually what all of these theories have in common. The scale of this new physics is not tied down. It's not, if you want one-to-one correlated to electroweak BEV, you could take supersymmetry and take the scale to be much higher. The seesaw model is already pretty, well, you can have it lower, but it's, or the one couplings give you a 10 to the 12 gig electron volt scale also, and GATs, etc. And that follows from all of the theories that coupled. Good to mention that that common property that they have is guaranteed by the decoupling theorem, that tells us that if the scale of new physics can be pushed up indefinitely, can be arbitrarily increased, there shall be no effects left at low energy when we take that limit, and one is left with the standard model, nothing but that, which is the self-consistent theory renormalizable that you're left with after you taking everything else to be very heavy. But like we were hinting in the Q&A session, the fact that the standard model does present, the SMEFT presents that limit, and all of those theories in SMEFT are obviously decoupling, that doesn't mean that it needs to be the only way to decouple. And we pose the question when we look at quotient theories in hep over SMEFT of, well, first of all, what do they look like? What type of theories can be found in here? And is there any such theory that does decouple and then presents a different way to reach the standard model? So I'll try to depict here this in this childish drawing. We do know that if we take the standard model road, excuse me, the standard model EFT theory, there's a road that leads to the standard model, which is as simple as taking the cutoff to infinity, and all effects disappear. Now the question is, if I take the heft over SMEFT road, this quotient theory road, where does it lead me? And is there any way, any kind of backdoor through the quotient theories to get to the standard model? Is there any other way to approach it that we still don't know about? And that's an open question. All present indication seems to say we don't have such a backdoor to the standard model, but I don't think the question is settled yet. And we can again capitalize on visualizing theories to see what at least these quotient theories could look like a priori. So we've already seen these theories here. Again, I remind you, gauge action is rotations around the axis in this space that we've reduced to be two-dimensional for visualization. And then this radial coordinate will be little h. And this sphere corresponds to composite Higgs models, or the minimal composite Higgs model. This flat case in there was the standard model. That again extends to infinity, will be a two-plane, and this is based on SO1,4 symmetry, for whose completion we don't have an answer yet. But then we could have theories of those two kinds we outlined. We could have a series of the type B, as we have here. Why is this the case? Well, again, theories of the type B present would be in fixed point or invariant point, which in this case will be this point here that goes through the axis. Not quite the axis. But if you look at it, it's a conical singularity, so it's not smooth around that point, and that will give us theories of the type B, as we've outlined. Theories of the type A are not hard to draw, they're harder to make sense of. But this type of theories on this side are both of that kind. Here the axis will go somewhere around there, and that point, that wolf invariant point, is missing because in this case we have a torus that simply doesn't go through the origin, or in this more hyperbolic-like case, we also don't go through the origin. This theory does not present, or in the language of heft, when we write our metric with, so to speak, the radial coordinate for the Higgs, and then there is that f² function multiplying what will be angles in this direction, those Boston bosons. And as we've defined it, So I'm saying U is in there. U of phi. These these Gaussian bosons always get rotated. They're angular coordinates, so that you cannot help it. They always get rotated. This is the way we're parameterizing this space. So for that point to be absent, what we should demand is that f of h is always greater than 0, or that no point exists such that f of h star equals 0. That will take us to the origin. So that's the condition for this type of theories applied to hep's. And in this case, we would have that such a point exists where f of h star equals 0, where all of those angular coordinates collapse, the origin indeed, but it is singular. Okay, and then just to mention this last theory in here, it's just a way to illustrate, in particular that green manifold, that you could a priori draw space that is at a finite distance from the origin, where the vacuum of the theory is, that could look increasingly flat. And increasingly flat is to say increasingly like the standard model, but still turn around before reaching the origin and coming back. And this would be naively a theory that would locally look just like the standard model, if we can really take this limit to be truly flat, but it never goes through the origin. So it's not really within SMEFT, it's a coordinate theory, and it's a candidate approximation or to the standard model locally, but not globally. So this, we wrote this down with the explicit f of f function in our paper as a candidate decoupling limit, but we didn't find an explicit way to recover the standard model still with it. But just to explore the possibilities, one should think of these type of theories, and as it happens, drawing them helps. Okay, so I'm going to see an explicit example. We're going to look at its phenomenology, and you're going to become familiar with it. For that, we need just a bit of previous knowledge, how to build effective field theories from ultraviolet completions. So we're going to consider a simple UV completion, which in certain limit gives us a quotient theory, SMEFT over hep. Oh, this is the other way around, hep over SMEFT. But you know what I'm doing. And not only that, in a different limit, it will return SMEFT. So we can, with a single model, explore both possibilities, and that'll also be nice for phenomenology, because we only do computations sort of once, and then we examine two limits. So as for the basics for obtaining EFT from UV complete models, we can assume we know the ultraviolet complete theory, and in particular the action for that ultraviolet complete theory, that we separate into light fields, phi, and heavy fields, capital phi. And the expression for the effective action at low energies is as simple as integrating out the heavy field with the path integral, when this means the functional integration of the heavy field, capital phi. And to first order in the loop expansion, this is substituting phi, the solution to the equations of motion for phi, back into our action. It will be corrected at loop level, but for our purposes, it's good enough to stay at tree level and obtain the result. More detail on this expansion, we don't want the most general of the full action at low energies, but really we want to focus on the metric, so the second derivative of the light field. And we can do an expansion in momenta, a derivative expansion in space-time momenta, but we don't want it expanded on little phi. We want the full metric. So we implement an expansion on momenta only, and we say that the ultraviolet action has component that does not depend on momenta at all. This will be the potential. Then a component that has two derivatives, momentum squared, and the same goes for the solution to the equations of motion that starts at zero order, then some p squared term. And in particular, this expansion applied to the equation of motion will tell us that expanding both on the action and on the solution, the first term is as simple as the variation of the action. This means variation of the action related to the field. As you know, the equation of motion comes from. And the first term is zero order in both the solution and the action. Now we can write that effective action at low energies to recover the EFT. Applying that same expansion, we'll have first the zero order term. Then for order p squared, we'll have the evaluation of the p squared piece of the action on the zeroth order equation of motion. And then the zeroth order action evaluated in the p squared equation of motion term. By in our expansion, this means might have created it. No. Expansion, this means the variation of the zeroth order action, because we expand times this first order variation. But this piece in here is precisely what defines the zeroth order equation of motion. So it does cancel out, because that is that right here. Equals to zero is what defines the equation of motion to zeroth order. What I'm saying is that the evaluation of the p squared term is as simple as taking the p squared UV action and plugging in the zeroth order equation of motion. So we only need one of those two terms. Good. Now we're ready to see these models that will build out of a UV theory with a Higgs tablet and a singlet S. This now is a singlet as most people will understand it, as real scalar field that doesn't transform under the gauge symmetry. We're borrowing this model from here, although with a slightly different notation. And you can see it explicitly here. It's nothing too exotic. It's the UV Lagrangian with the kinetic term for H and the potential, which is the generic renormalizable potential that you get if you impose a set to symmetry in this guy, just for simplicity. It's a set to acting on S, so that we can have Higgs tablet squared term, an S squared term, a mixed Higgs singlet term, and then quarterly couplings for each of them. What we will assume, though, is that with this notation, notice that these three terms have a negative sign out front, and we're assuming all parameters greater than zero, both S, both the singlet and the doublet, get a vacuum expectation value. We can then obtain the effective action or effective field theory from this Lagrangian with the procedure that we just outlined. This is what the zeroth order equation of motion looks like. Neglecting momentum, you just come out of taking the variation of the potential with respect to the field S that you can do yourself. And from this point onwards, but basically, this is all a big do-it-yourself exercise that is laid out in the notes, and you can, all of these steps you can do yourself. Right, so we have that this scalar singlet takes a BEF, stays at some finite distance from the origin, looks something like that, its potential, and that distance is given by both that M2 term, that M2 squared term, and the BEF that the Higgs tablet takes in there. All right, so from this zeroth order equation of motion, given that we do know they take a hep-ph, we solve this equation by canceling this term here. And this gives us the zeroth order equation of motion as a function of the Higgs doublet there, and also the masses and the whole thing square root, as you can again derive yourself. Now we're looking at the p-square order Lagrangian that will come from kinetic terms. We'll of course have that doublet kinetic term that we saw, and in here we just substitute this solution for the singlet S. This is what you obtain in terms of the doublet. Then we write down again that the composition of our doublet being equal to V star plus H underline over square root of 2 times U 1, and that gives us that second form. Right here, that second step. Now this looks a bit closer to the metrics we were using, with a term for the costons in here, and the kinetic term of the Higgs, H underline here, which itself is not canonically normalized, but it has that extra piece in there. And we also note, since we're at it, when we rewrite this full term, we will use some of the equations that we used in yesterday. We call this new metric in H underline coordinates. We simply say that it has a coefficient for the Higgs kinetic term, K of H, and then a coefficient for the costons, that in this case, because it's simple enough, and the expansion around H equals 0 will give us the normalization for the costons. It happens that V star equals V in this simple example. This looks very much like the standard model case. So that part of our Lagrangian looks the same, and we can set V star equals V, 246 electron volts, giga electron volts. And then that other step that we had in the last lecture was converting back to our frame and rewriting the curvature invariants that we wrote in terms of derivatives with respect to the underline H coordinate, as in here. This is actually a special case of a formula that we derived last time to relate a metric of this type and a metric of this type. In particular, f of H is simple enough that just reads V times f of H is just V plus H. So it only has first derivative, it doesn't have second derivative. So the only derivatives that show up in here are with respect of K with respect to H underline. And this will give us curvatures R phi and RH, which we can then find explicitly. Again, all of this I encourage to do yourselves. It will look something like this. The curvature for phi, which remember is related to the scattering of boson bosons, is proportional to the lambda tilde square term. That was the term that mixed the Higgs doublet and F. Then lambda was the term that the quartic coupling for the scalar S, and M2 was that mass that was out front. This also had a minus sign, and this has a plus sign for us to be, for the potential to be bounded. And then the dependence on the little h underline is here in the denominator in this case, and you can find the expression for R sub h curvature, which is related to scattering of Higgs and Goldstone bosons, and this other expression. And this is really specifying the EFT that comes out of this model. And that's all we need for our analysis. All right. In particular, we can expect two limits that will give us two different effective field theories. One of them is slightly more familiar. If we take the mass of this mass M2 to be much larger than V, then you can expect, at least naively, the mass of the singlet S to go to infinity. You can work this out explicitly from the potential. And we have that in that case, as you can again check yourself, R phi and RH correlation that we recover is that of this method. This is the limit, not because I'm telling you it is, but because you can check it yourself. And in particular, R phi equals RH in that limit that you can maybe see yourself. So we can apply now an expansion of 1 over M2 squared, and that would give us the very same Smith expansion in that limit. All right, so that's perhaps not so surprising. This model has a limit in which we can take one of the masses very large and should decouple as the Appelquist-Karat-Sonnet decoupling theory tells us. But if we look at that other limit, in which we set the opposite limit in that sense, we set M2 to 0. This, first of all, doesn't mean that S becomes massless. It's still not massless, because remember there was still that coupling H dagger H tilde times S squared. So even if we neglect M2 S squared, when this Higgs takes a bed, and it does, and as we know, it's proportional to the electron weight scale itself, there will be a mass contribution to this scalar singlet. So it is still an EFT. We're integrating out a particle that has a mass potentially larger than that of the Higgs, and that's what we're assuming implicitly, actually. But it's also true that if you look at this curvature in particular, if we get rid of that mass in there, all we're left with is this other term. So R phi will read lambda tilde over lambda tilde plus 2 lambda E plus H squared. And now what should worry us about this form is that even though these theories seem to have a candidate fixed point, and indeed we can look at it and find it from the coupling, sorry to go back, but the coupling to the gallstones, we said that when it potentially vanishes, that's a fixed point, or a candidate fixed point. If we stare at it to have this equals 0, we would need H equals minus B. So that's a candidate fixed point, and it is indeed always for this Meft case, and there's no problem with it. But if we now substitute that in here, we obtain infinity. So it blows up at that point. That would be a candidate fixed point, and it's not a fake singularity. It's a true singularity. We've just seen that these curvatures do really tell us about the scattering around different points of the manifold. So that is a true singularity, and we've encountered is nothing but a theory of type B, which has a candidate fixed point, but it is singular. You cannot expand around that point, things blow up. And we've recovered a quotient theory or hep-ph. So there you have it. It's not that mysterious. One can see one of these theories explicitly and try to work with it. Of course, what we have to do is never approach this point in this theory because it will break down, but that's fine. We're expanding around the vacuum, which is H underline equals 0 anyway. So at least in the neighborhood of the vacuum where we live, we're still safe and we can expand. And then finally, the other thing to be remarked about this theory and connected to the decoupling theorem is that this analysis tells us that the mass of the singlet square will go with lambda tilde over b squared. And this is an explicit example of this theory not decoupling, because this square is really 246 gigaelectron volts. So the mass of the singlet that we're integrating out can only be as large as allowed by so you cannot push this coupling arbitrarily large because it will give you probability larger than 1 the scattering amplitude. There's a bound on this. So we obtain a finite cutoff theory, confirming both of our intuition or suspicion about quotient theories, hep-ph, that they don't decouple and the spectrum is bounded from above. And in particular, we put these bounds explicitly, we'll find that that bound will be something like 4 pi over b squared if we use partial wave amplitudes and perturbativity argument. Great. Now, just some few quick words of phenomenology. I'm really not doing it any, giving it any fair treatment. There's so much more to phenomenology in heft and in SMEFT, and hopefully Professor Chart is covering some of that. Let me just mention that the possible physics that heft covers goes well beyond what you might expect. It's not only about high energy conditions, but these are truly modifications to the couplings in the spirit of EFTs. EFTs just have the same matter content that you know about, but couplings that you wouldn't think of with your simplest theory, with the standard model. And there can be new effects in a lot of places. You can have, for example, baryon non-conservation processes, like this vertex here that you can imagine at LHC, for example, violating baryon number, as you can see from the lines in there. Well, this has a lot of interesting physics in flavor and flavor violation, as a long-standing disagreement in the measurements of semi-leptonic B quark decays. There's also more collider-related vertices where large deviations are allowed in heft, 3-point triple gauge vertices and others. But there's also low energy observables that you might not think of initially. You can have CP violation showing up in the form of a neutron electric dipole moment. That will be a coupling between the spin of the neutron and an electric field. And you can test for this as simple as having neutrons capture somewhere with their spins aligned in a given direction, and then apply an electric field in one direction and another and compare their Larmor precession frequencies. Because these guys, if you have a magnetic field, would precess around the magnetic field direction. a coupling between the magnetic field and the spin is fine, it's not CP violating. But if there's also any difference in the presence of an electric field, there'll be CP violation. And this could be a good test for axion models or any other explanation for the strong CP problem. But to put the finger again on the difference or differences between hep and SMEPT, what we saw in that expansion discussion is that hep allows for large deviation from the standard model. So you could have, for example, that these supple couplings are larger than you're getting generically in SMEPT or other observables, for example, the kappa framework, which is just rescaling standard model of cross sections and observables with a factor k can be accommodated or can be given a proper theory background in heft. And then the other generic feature of heft is decorrelations, as we've seen. You might have that observables in SMEPT as large as it is and as many parameters as it has. Some observables might be correlated with one another, and we saw an example of this with curvatures. So that's an explicit example of correlations in SMEPT that are lost in heft. So we can look for deviations of those relations to see heft is out there. As it happens for that very example where we mentioned that curvatures control longitudinal W boson scattering, in practice, looking for such scattering is complicated experimentally. There's a lot of backgrounds. So rather than using that scattering, we put bounds on the curvature from the Higgs coupling on the linear level to electroweak bosons from vector boson fusion and the absence thus far of Higgs production. Those are related to F prime and F double prime in our action, which in turn give curvatures. So it's sort of an indirect bound on those curvatures through what we know about the Higgs so far, but it gives us bounds on curvatures, which we can put together into a plane of both curvatures. This is what I give you here and what is also in the notes. So here in the Y, in the x-axis, we have the curvature in the phi for the bosons, that definition times v squared, that's 246. With electron volts to make it a dimensionless direction. And this other direction, we have R sub h related to Higgs and Goldstone boson scattering. In this curvature plane, the standard model lies at the dead center. No curvature in the standard model is the flat case, so that's where we're at. And as current status of experimental data shows us, stronger bounds are to be found in the direction of R phi. Bounds from F prime, for example, that coupling here of Higgs are quite strong and bound this dimensionless magnitude with present LHC data to exclude all of the red regions. So all of this is excluded by current LHC. Probably good to say it explicitly. With the blue, we will the blue will be explored or excluded by high Lumi LHC. And future experiment, future collider proposals will further zoom in and exclude all this green region. That's a terrible color. FCC, for example. So that we will be closing in further and further into the standard model. And this is just a visualization of this experimental bound. So as the final exercise, or sort of things for you guys to work out, is to look at the phenomenology of that case study that we were looking at. In particular, for both cases, you can think of plotting. This is like a droid, like a coloring book for you guys, but just drawing models. So you can first, for each of these cases, try and draw what is the RH, R phi correlation. Because they're correlated, that means that it will be a line somewhere in this plane. What does line look like in each of the cases? Because both cases have specific predictions for the RH, R phi correlation. So you can, with a little skill, just draw it in both cases. Then try and think for each of these models if the decoupling applies by simply thinking about any possible obstacles to taking the curvature equals to 0. Is there any obstacle here? Is there any obstacle there? And for that, you can explore and go back to the model explicitly and find out what is the explicit expression for the mass of the singlet that we're integrating out. And for that, you can first, or you should first expand on the BEF that it takes. And then around that point, find, after finding V of S in terms of the parameters in the potential, find the mass of that singlet S and think about that limit together with perturbativity constraints on lambda. So you can take, as I mentioned before, lambda and lambda tilde smaller than 4 pi as given from perturbativity terms. Get rid of this guy. All of this discussion of who's what can be found on the notes. And that way you'll get familiar with what these things look like and how could we potentially tell them apart, addressing all of the questions that we brought up. There are general theorems about the non-decoupling of hep over SMEP theories of the type B that I don't have the time to go through here, but I think seeing an explicit example is a better way to teach you how things work. And that's really all I wanted to say, and I think you can use a little break between this and the next lecture, so let me summarize and finish up here the series of lectures. So we started by a bottom-up approach to elementary particle physics. We just took into account that the W and the C bosons have a mass. We need Goldstones for that. We included the Goldstones in the form of the matrix U. And we realized that theory had a unitarity problem or had a finite cutoff at 4 pi V. We needed a new particle. The Higgs particle was just the candidate to do the job. So we put it into our Lagrangian and we realized in a certain limit of that Lagrangian, we could recover SMEF, which is therefore embedded in heft. And we went on to discuss the differences between the two. In this very last lecture, we found that lemma that helps us tell them apart. We've also seen how geometry for field space is quite useful, and it allows to discuss scattering in terms of geometric objects. And finally, the encouraging word for experiment in all of this discussion is that if truly all of these quotient or heft over SMEF theories don't decouple and have a finite cutoff, and that finite cutoff is indication that cannot be any larger than 4 pi times electroweak hep-ph, not much larger than the tera-electron volt scale or so. That is a nullus theorem or a guaranteed target for colliders, which can be part of the legacy of the collider program of our era. And yeah, I'll stop it there. Thanks a lot for your attention, and I hope you enjoyed the lecture.
Any questions? Rodrigo?
Thank you very much for the nice lecture. I have some nice question about the UV completion of your EFT in the viewpoint of geometry prospect. Let's say. So it's your UV completion is, we can think like kind of embed your theory to embedding the high dimension field space. Is it correct?
Yes, that is true. That is.
And also, I remember, if I remember correctly, the curvature of the field space is related to the color scale. So
It's related to?
It's related to the color scale of the EFT or
Yes.
And is it guaranteed that any EFT can be embedded in the high dimensional flat space, or if now we can use some we can state that, like, I mean, we can distinguish which one can be UV completed and which one cannot be UV completed, like the swampland program or something.
Right. That's a very relevant question, and perhaps for the same reasons, a very hard question to answer. There's perhaps because of our limited resources when building models, all of the UV completions that we've built so far are weakly coupled and are things of this sort, like adding up some SU2 representation with another one and integrating one of them to be left with an EFT that, even though from the point of view of the ultraviolet, is just linear representations of our group. From the EFT point of view, when we integrate them out, we obtain curvature, we obtain a metric that is non-trivial, and those examples also include, as we have in here, modulo theories, these quotient theories left over heft. And I suspect that that is the reason we only found UV completions for theories of the type B, with a singularity there that this type of theories give us, is because we're considering only weakly coupled theories. So all of these are implicitly assuming that, well, we are assuming actually that these couplings are perturbative so that we can expand on them and obtain a convergent series. But I would suggest that if we consider UV completions that are not necessarily weakly coupled, we may get, well, first of all, UV theories that themselves have a curvature and some non-trivial Riemann tensor, and when integrated out, that gives us further curvature in heft. Now, having said that, that would be postponing the problem, because if your UV theory has curvature itself, it means that it also has a another cutoff. So maybe you're just postponing the problem a bit further up. But even that intermediate step, I think, will give us potentially theories of the type A, which will be something new we don't know about yet, and the possibility to discuss, explore all of the possible heft over SNEP space, which for the moment, I think we only have a good handle on weakly coupled theories and these type of theories with a singularity. Yeah, I hope that addressed the question.
Any quick question? Okay, well, considering we have a seminar coming up, let's thank Rodrigo for all 4 of his lectures this week.